I'm Dr. Bhargav from the first year IIM Tech, and I'm presenting the next speaker for today, Dr. Ramamurthy Badrinath. Dr. Badrinath is working as a principal engineer with Ericsson Research, Bangalore, where he is the part of a team that deals with the management and operations of cyber physical systems. He has earlier worked with HP in various areas, including cloud and high-performance computing and the semantic web. He has also been the general co-chair for the IIIT HIPC conference for several times over the past years. Prior to his joining the industry, he served as a faculty at IIT Kharagpur for 9 years, where his core area of research has been graph theory and the interconnection of networks. He is also currently a visiting faculty at the Indian Statistical Institute, Bangalore. We are really excited to hear from Dr. Badrinath his talk, IoT from Data to Action, which is going to be centered around the hot topics of today, IoT, machine learning, and artificial intelligence. I would request Dr. Ramamurthy Badrinath to kindly deliver his talk and enlighten us.
Big thanks to Manisha and the other organizers of this event for inviting me. It's really a pleasure to be here. I've been here a couple of times before, and it's always a pleasure to talk to this audience. So I was wondering what to talk about, and so I'll sort of transport you to a little bit of the engineering world. So what you'll hear about today is a few things that my team here have been working on over the past 2 years or so. It has to do with IoT. Like the person who introduced me mentioned, IoT is a very hot topic. Everybody's talking about it. So we also wanted to figure out what it means to us. Right? So we were, I was not an IoT person. You heard a little bit about me. I didn't know anything about IoT. So I wanted to figure out what IoT meant and how we could be relevant in this context. So this talk is about investigating what IoT means and what some of the gaps are in terms of, everybody talks about IoT, but actually there aren't that many applications around. So we look at it from an engineering perspective, so it's a very engineer's perspective, and we'll take a look at what technologies are missing and what technologies have not been employed, and probably they should be employed. And there's a lot of evidence, so I'll show you some evidence from the point of view of standards committees and so forth, that actually people are thinking about these things and they're not purely theoretical. Okay, so towards that, it will be a very introductory talk in several aspects. I won't go very deep into stuff, stay at the big picture level, though I'll be talking purely on the technology aspect. So IoT has a lot of non-technology aspects to it. A lot of things, people will say big data and a lot of stuff. I will not be talking about that. It's very technology focused, and I might point to some resources where I'm not, the person to talk about it. All right. So roughly, the big picture is the outline of the talk is a few definitions that, from my perspective, everyone has their own understanding. Then I'll talk about 3 pieces that I think are interesting. One is data. The other thing is what I call planning, and I'll tell you what that is. And the third thing I'll talk about is the actual IoT devices and so forth. So I'll talk about these 3 things and then summarize. Okay. So IoT is, in some sense, all that IoT is a source of data. That's not the full picture, it's half the picture. And so it's a very important source of data, and that's what makes IoT very, very interesting. We all had sources of data, but IoT is a very interesting source of data. We moved from enterprises having data to perhaps Twitter and all having data, and then sort of we're moving to something else with IoT. So that's roughly what's happening. And what this gives us an opportunity to do is it gives us an opportunity to observe the environment in ways that we haven't observed before. So that's the big difference between the enterprise data that we were getting and the kind of social media, Twitter data, and the kind of data that I call IoT data. So it means that we have a way of observing the environment. We have data points from the environment which we didn't have even 5-10 years ago. We have lots of data points from the environment. And what humans do is we observe the environment, we act in our environment, we experience something and we learn. And that's how we derive value from the environment. Or that's how we derive value from what we, if you think of us as the receiver of data from the environment. So it's a vast environment giving you lots of data. That's us listening, and that's us reading, and that's us seeing. And we get a lot of data. And what happens is that we learn from this data, and that's what makes us. To a large extent, we are a significant product of what we observe and what we learn from our experience. So we interact with the environment as well. That's the other part of the story. We interact with the environment, and there's something called an experience that we get, right? So it would be nice if, since we have an instrumented world, that we are able to collect this information and give it to a machine, right? And the machine would try to do something like this. So what does that mean? Okay, that's the question that we are trying to ask. What does it take to enable that? We have good, interesting stories about all these machines, like the Terminator and all that stuff. But let's think more down to earth. We have lots of data coming. What nice stuff can we do with this data? So as far as machines go, yes, machines are programmed to act in the world. So that's actually the way I see it, right? One way to say it is machines are passive receivers, but really what happens is the machine does nothing. Like, we program the machine to do things, and then it does things. That's the way I see it. But what would it take for the machine to actually get a lot of input from the environment and actually do something with that input? What would it do with the input? So if you give the machine a lot of data coming from cameras, and so what on earth would it make out of it, right? How would we write programs that made sense out of the data that we get? So this is sort of the starting point of the question that we want to ask. Of course, the idea is that man does this all the time, and perhaps if we could do this, we would get what we call potentially autonomously operating machines, right? And that's what people normally associate with robots that go around doing some things and so forth. But I'm using it in a slightly general term. If the machine could understand, there's one piece missing here, we'll come back to later, but if it could understand, then it would probably autonomously do things. That's the hope, right? But we're very, very far from that, extremely far from that. But what I'm trying to say is, I'm trying to say what are the technologies that take us there, and what is the state of where we are on that journey. That's what I'd like to explore. And of course, if we did this, then we'd call this artificial intelligence, right? That's what people call artificial intelligence. So artificial intelligence is, you've already heard, for example, that I think a lot of these Google type companies, right? They are big because they have access to data. And we've heard that again and again, right? It's not the cool learning algorithms, but it's actually the access to data. And sort of what we're trying to say is, what does it take if we had access to that data? All right. So on the one side, people think of IoT as actually, there are a lot of people who will say IoT is actually a problem. Okay? That's because we don't have methods to actually take all the data that's coming from the devices and do anything useful with it, right? When we see, we are constantly seeing people, right? So I see you, and then I forget, and then I meet you in another meeting, and then did you come to that, things like that, right? But what do machines do? How are machines supposed to handle that? So scale of data is a challenge. And of course, we can't really get value out of all the data that we collect. So if we collected, let's just say, for instance, that we collected information about everybody in this room, right? Lots of information, and put it in some form, right? Then you could ask the question, what do you do with that? And you could collect more detailed information, right? And what did you do with that? Would you do anything more with more detailed information? So there is a challenge in terms of what value we can derive with more and more data that we are able to collect. And the idea is that the AI technologies are supposed to help fill that gap. So if somebody thinks, what is AI going to do for us? One way to look at it is, it's trying to fill this gap. We do it with our maybe NI or whatever. I don't know how natural this intelligence is, but at least it's not as artificial as this is. But AI is supposed to fill that gap. That's another way looking at AI. But interestingly, I told you about Google and so forth. Actually, the huge amount of data that comes out from IoT actually turns out to be an opportunity, right? Because you learn from more data. So it's interesting. So it's actually good. So it's a problem that we are supposed to solve, and AI is a technology that needs the data in order to make any progress. So it's a nice situation that we have. Okay, so going back to what data looks like, right? And what this IoT stuff is all about. So right at the bottom, what we have is we have a bunch of devices. Okay? Nothing unusual there, and they give you raw data. Okay? Right. So this is like temperature values coming from some sensor here. Okay? And then at some point of time, you analyze the data, and this is when you start slowly trying to make some sense out of the data. Right? For example, oh, this data is right, it's not right. I mean, this is in Celsius, and so a little bit of it's still at the data level, but maybe you do a little more. You derive some statistics out of it and so forth. And then at some point of time, you want to start connecting it to higher meaning. Okay, so you say, okay, all this data is fine, but I somehow want to add meaning to the data. Somehow, we are able to look at the temperature and say this room is this hot, right? So it's a small elevation, but it's actually a big thing in terms of the technology we have. And then we put this information into what we call a knowledge model. That is, we have an idea of what's a comfortable temperature for a person or a room or whatever, and then okay, this is slightly off that mark, or maybe it's inside that mark. So we put it in a slightly larger context, and we try to think of these as what are the related pieces. There are people who are sensing on their skin, there's a temperature, and then maybe it's comfortable. You're deriving more facts than immediately what data you have. You derive more facts than what data. So that's what we mean by knowledge models. We create this connectivity among these items. So there are a bunch of technologies to do that, and all this doesn't make sense unless you do it for a purpose. Right? So that's what I mean by an application context. That means, for example, if you took the previous slide, we said AI is intelligent, it should be intelligent, it should interact, it should learn. But if you don't know what purpose you're learning for, it's not always clear you can do it. At least when you act, you need to be acting for a purpose, right? You can't act randomly. Maybe you can get data passively, but when you act, it must be towards something, right? You must turn the knob left or right. So it means you're acting for a purpose. So there's an application context. So from an engineer's point of view, what we want to do is we want to look at this stack and say, aha, so I want to go from the devices that I have to this application context. So I want to do something. Right? So the application context is I want to do something. I want to do something and I'm getting data. And what I'll try to do is I'll try to paint a bunch of technologies in this stack that tell you, how we are going up this stack and what the state of the technology is in terms of what engineers are doing in order to bridge this gap. Good questions are, have engineers realized that this gap needs to be bridged? That itself is actually a good question. The other way to look at it is a lot of people say now we are moving to data-driven technologies, and this is my take on what it means. At least for me, as a person who's working in this field, for me it means how can I take data that's coming from the devices and make applications decisions, right? And there are and if you're an engineer, there are many other facets that are not represented here. For example, I can't make an application for a very dynamic environment. For example, tomorrow I may come and put 10 more sensors here, and then I have to go and change the application. As an engineer, it's a painful thing to do. And with IoT, it's very easy because all of us carry devices, and when we come to the room, all of us add new devices to the device set here, which can give you information. So it's a very interesting mix that we are talking about. Very interesting engineering problem. Data is the main thing. However, what this picture tries to show you is that it needs to be lifted to some level before it becomes useful. So that was my purpose here. And we'll come back to this picture and we'll throw in some technologies. Now I'm going to take the opposite end and look at it from the context of applications, right? So these AI guys, so there's these device guys who've been manufacturing devices, right? And they do very interesting stuff, very cool stuff, control systems and so forth, very interesting stuff. And at the end, there are these people who talk about AI technologies. So what I'll do is I'll just broadly sort of classify these technologies into some pieces. Just, all classification is just for understanding, right? There's no hard and fast rule. So one is AI uses a bunch of technologies that are basically for inferencing, right? So if you have facts and if you have modeled facts in some form, for example, you could use logic type of systems, with predicates that say this is true about the environment, this is true, this is true. So for example, if you had a person move in with a new gadget, you could say it's true that this new gadget is in this room, right? So you have a lot of assertions, a bunch of facts. So if you could, what you can do is you can basically derive new rules from this fact. And this is very useful, right? It's very useful to pre-build a bunch of facts into the system. Right? And then that's how, for example, a lot of the hard coding that we do is about some facts that are in our mind. And as opposed to that, a language like Prolog is where you declaratively put all your facts. So if you're familiar with Prolog as a programming language, you don't say how to solve mostly, but you say what you want. So you give it a goal or something like that. Yeah? So and then under the covers, that means that you have a bunch of search heuristics or simple graph search type of heuristics that help you in reasonable time arrive at some conclusion. So that's what logic-based approaches do. And then there are these approaches that are nowadays very popular, right? The statistical analytical approaches, right? This is what we call data sciences. Lot of words to this. Some of it is called regression, some of it is called predictive modeling, right? So all this is about, the one word I want you to take away from this is, it's all about having a model for the data. Once you have a model for the data, you can do inferencing. Okay? Inferencing works on models, right? There's still a lot of debates. Are these correlation models? Are they causation models? Very interesting stuff, debate still exists. But what we'd like to do is we'd like to have some kind of model for the data that we have. So this is very interesting, right? You're getting a lot of data and you're building a model. Right? Statisticians have been doing this, and computer scientists have invented their own ways of doing this. But the point is that we can elevate, we can lift data. So this is the part of the lift story, right? So we have data, we have lifted it to a model. A model is, it's an abstraction above the data. It's telling us more than any individual piece of data. And of course, there are these whole bunch of technologies that are becoming more popular today. And in some sense, they fit this model building concept, right? They also help us to build models, but they're based on what we call neural networks, or the computer scientist version of how the brain does things, right? At least one version, right, is called this connectionist approach. And this is often used because there are certain problems like perception that we are not very good at. If we try to code, take an image, do segmentation, it's very difficult to, this set of segments means it is a crow or something like that. We're not very good at that. So what we do is we use this connectionist approach where we actually don't have an explicit model, sort of, right? It's very difficult to reason about the models that these guys generate, but they generate models that can be used for inferencing. So generate a model, and then if you give me a new picture, I'll tell you, the model will tell you if it's a crow or not, but you can't really understand what the model is. So it's sort of a little disappointing, but we'll come back to this. And this is an important, it's an important thing to think about, and we'll come back to this a little later. And the other thing other trend that's going on here from an AI person point of view is all these were seen as special purpose technologies, right? At least going down, it's quite special purpose. You build something for something, right? You build a AI to do NLP, or you build an AI to recognize images. So they are all specific to some stuff. But then we are trying to move towards general purpose AI. That would be a good goal as a computer scientist, right? What does it take to build a general purpose AI? A lot of nice, interesting questions there. But at least what we are seeing from the trend is that the technologies are actually driving us towards that. And we probably don't have enough tools to understand or to uncover what it takes to build a general purpose AI. So that's where all these people are starting to talk to bioscientists and so forth to understand maybe there are other models of how things actually, how models are built, right? All right. So first I'll talk about, again, I'm coming back to the data side of things, and we'll talk about, for example, you know that we have Twitter feeds, and we have all that kind of social data, but we also have a bunch of enterprise data, right? These are all disparate sources of information, and of course IoT. So the point is that we have these sources of data, and they're all arriving at you at some pace. And while it's easy to program a computer to do something, because it doesn't have to think, it's always an input, it's a transfer function, generate an output, right? But what we're interested in is that it does some learning. Okay, so what is this learning that it does? So can we understand a little more about that? And in order to understand that, what we need to do is we need to understand the larger context in which. So if you want to do that thinking part of the loop, the one that I had in blue bubbles in the downside, what I need to know is I need to understand this in the context. So just like I told you about the temperature sensor, we need to understand this temperature sensor is telling me about, maybe it's telling me about number of people in the room. We as humans can interpret a lot more from what a temperature sensor is telling you than the fact that the temperature is, some 26 degrees or whatever. Right? So we need to build these models. They could be mathematical models, they could be any other model, but they need to be some kind of a formal model that we build from the data that we sense. Okay? And this is what some people do very well with statistics, and the connections model does well, but we've not been able to lift it much beyond that actually. Right? So there is some kind of a gap there, and I'll show you a little bit about that gap as well. But what I'd like you to carry away is, when people talk about AI, what you're doing is you're just building models. That's all it is. So you build models. There's a phase when the model is built. That could be by somebody supplying you information. It could be by some learning or whatever that's called. And then there's a time when you use that learning. There are two parts. So there's the inferencing part where you use it to say if the new picture is a crow, and there's a part where you learn. And sometimes these go hand in hand. But all that AI is about is building models. So now I need to think in terms of that stack that I have, right, from data to application, where this model building happens. So some of what I show you will be about that. Just to put it into context, building model from data could mean things like getting a lot of text input, right, from books. And what we do is we probably put them into what we call standardized vocabularies. Actually, we use some, standardized vocabulary is like a dictionary where we have all the words listed out and then many meanings listed out, right? But actually, we in computer science, we'd like to do something better than a standardized vocabulary, right? For example, because there are a lot of relationships that are there that we want to infer about. So what we do is we don't have a dictionary that means you can read and it's standardized, and if two things point to the same thing, then they mean the same thing. That's one way to do standardized vocabulary, and we do that every time we want to translate between, let's say, two protocols or two languages or something like that. What we do is we use this thing called an ontology. So an ontology is more of a formal representation where you have an opportunity to embed relationships. So you have facts. So you have an ontology which says what it means to be, A is the brother of B, and B's son is C, so C's uncle is A, right? Now you just say this once, but you can later interpret that, such and such a person was actually Mahatma Gandhi's nephew, right? You can interpret that from the fact, though that fact is not necessarily declared. So ontologies are sort of like slightly elevated vocabulary, so they do standardize information, but they also have this additional facet where you can add relationships that you can exploit to information. So that's not a new technology. It's been there for about maybe 15 years or so. It's been used a lot, but still there are a lot of challenges in terms of efficiently using ontologies. So that's still a problem. But this is quite popular, and people have built nice graphs out of these. This is what goes behind DBpedia and so forth. So for example, today if you click for Ramanujam, you'd probably, on Google, you'd probably not just get 20 links with Ramanujam, but you'll get something on the side that says, here's Ramanujam's photo and he was born on this day. It's actually very structured compared to, and they use technologies like this. So they are actually building an interesting model of the facts about Ramanujan. So slightly low level, we would like to be much higher than this, but it's a good start. So that gives you a feeling of where our technology starts. Okay, so we'd like to derive new facts. That's when a model becomes interesting, and I just told you a little bit about that. So this problem about using, for example, ontologies, we could use any other representation. The idea is to have representations which will allow us to reason. And so that's why there's this whole field in computer science of knowledge representation. So can I represent knowledge in a fashion that I can derive interesting information from that knowledge? And one example I showed you was taking a lot of information from here. The reason why I put these pictures here and not just some facts is that a lot of interesting AI goes into just doing this translation. For example, this is a table, right? And it's handwritten by somebody. So there's a lot of perception type technologies that goes into just translating a table into some fact that fits into. Interesting. So it's not about the AI that does the reasoning and so forth. So there is a little bit of AI that does interesting reasoning, but just getting the facts, creating the model itself requires a lot of interesting AI. So AI is used to use the fact and do something interesting, but also used to just create the basic facts itself. That's pretty interesting. So that part I told you, looking at books and generating some information, that is also often called information extraction, and that's a lot of AI cognition techniques, the audio visual cognition and so forth. All of that is currently, that's what it's doing. It's able to take the data and elevate it to a certain level. Right? How high it elevates it, it all depends on all the stuff that's sitting on top. But we have enough technologies to now recognize, I believe, photograph, face recognition technologies work better than humans or something like that, right? Some fact I read. So we're able to do that pretty well. So we're able to bump it up reasonably well, right? But it doesn't go all the way. On the other hand, we have technologies that are able to talk about things like ontologies, where sometimes we get knowledge from below and we populate it, and sometimes we, as people who know, actually declare facts, which is a good thing to do. If you know facts, declare facts, right? You don't have to stress yourself on cognition, right? Just like we tell children something, right? So they learn by that way. But then there is this whole stuff on how an application should be organized, which means all the stuff that you may have heard. Sometimes I used to find it quite boring, this stuff called workflows, when I initially learned about it. Yeah, do this and then do this. But the point is that workflows are a very interesting way to organize applications in order to do something. Right? That concept is there in the notion of a workflow. So we'd actually like to take device data and elevate it to workflows. So in some sense, that's what we're all trying to do. Take device data and elevate it, create a workflow from the data. That would be interesting to do. Right? And then from a technology point of view, we have these PDDL models that I'll talk a little bit about. We have these linked data stuff that can take different ontologies and connect them together and give us nice knowledge representations.
What is the underlying structure? Is it English verb, noun structure?
Yes.
Or some other structures?
It's the underlying thing is some kind of logic. Right? But on top of it, you could put, for example, you could try to fit English into that. It all depends on the language also, right? Not every language would follow a very logical structure.
Sanskrit will have everything which is native to Sanskrit has a, everything which is native to Sanskrit is derived from a verb. So action is primary.
Right.
In many of these, in the type of knowledge system which is propounded. So are such issues currently being dealt with in the applications being done these days?
Okay, so there are two parts to that answer. One is the ontologies, the way they have been developed, it looks like it's more based on logic and relations and predicate calculus and stuff like that, right? So you take your grounding there and then you build it up. So that's one thing. So for example, how do you represent actions in that context is an interesting question, and that has not been very successful. So if you look at the ontologies that we don't have great ontologies for action, because the actions are very interesting. Like, they're not just static facts, they have effects and so forth. So they're very interesting, and I don't think there's enough good stuff on that. The other part of the answer is that there is currently work, there's a bunch of people working on, I don't know how relevant it is to this discussion, but on looking at, for example, the formalisms in a Panini type structure, whatever, to see whether you can derive something from this. So there is some work happening on that front. I don't know how mature it is, and that's, I hear about it in bits and pieces. I would like to get myself a hand on that work. So, but there is something happening on that side. So if you're thinking that there's some inspiration to be drawn from that, I think you're right. That's my understanding. Okay. Okay. So then there is this whole stuff on what I call interactions. Okay? So this stuff isn't as fancy as AI and knowledge modeling and all that. So it's not very fancy, right? But it's the thing that real engineers bother about, right? They think about protocols. They think, so you want me to turn on the switch, right? You decided. So how do I turn on the switch? Right? You need to, and you can't tell me for every device how I turn on the switch, right? It will become very painful. Then I'll have to know hundreds of protocols, right? I need to know somehow. I need to elevate. In some sense, it's about abstracting actions as well. So people have tried to work on this side. So they've developed what I call protocols, device models, and slowly these people are also realizing that they actually need something more than what they have. So they've started with something called markups, okay, which take device models and protocols, and I'll talk a little bit about that. Hopefully I'll get time to talk about that. And they try to slightly say that, I can't tell you everything about, here's a device model. I can't tell you everything formally, but I'm going to give you a link, and you can possibly link to an ontology that will tell you more about it. So slowly you can see that the device people who are probably, they'll balk at you if you talked about things like knowledge representation. They're very interested in, here's a protocol, how much can I reduce the communication so that the energy gets reduced. This is the way they talk, right? And so they'll be totally put off if you say, you have to add so much of ontology stuff, because it doesn't contribute to the actual execution. It's fluff on top from their point of view. But from the point of view of the guy who understands what he wants to do, for him to take action, you actually have to elevate the device as well. So actually we are living in a very interesting time where we have all this data science that can do interesting stuff with the data. We have AI techniques that can work at a very high level, right? And then we have these protocol guys who are slowly realizing that to build complex applications, and in fact the guys who are driving this are the IoT people in the community, right? Because they are the guys who are dealing with huge number of devices, very varied devices, lots of them coming and going, floating populations, the same devices being used for multiple applications. They're actually going through a lot of frustration. They have to update the devices every now and then. They are the people who actually they're yearning for something to solve that. They've been trying to do it through standardization, and that has worked to some extent, but you can now see a bunch of effort that's saying, hey, let's add semantics to it, and that's going to help us. So we're actually living in very interesting times. I'm not sure why I have this, but we'll just go with this. I think I had this because I wanted to tell you that a lot of the cognition problems that we talk about, they use a bunch of technologies which is not my domain of expertise. But I just wanted to sort of ground you and say, if you see these technologies in terms of the stack that I showed you, most of them fit in the bottom of the stack, where they help you take data and build models. And you've seen me say this several times, so I'll not talk about this. But there's one part here, the thing on the right bottom here, which has a very interesting role to play, right? It's also a technique to take data and pop it up into knowledge. But it so happens that this technique on the right helps us also, in addition to doing its stuff for the regular stack, it actually helps us understand actions. So that's a question that we had here in the audience, and it's a question that I'm also asking, and I'll tell you a little bit more about that. Yeah. Okay. So beyond cognition and beyond understanding everything, that reinforcement learning is one of many techniques that will help us do what I call closing the loop, right? So remember, do whatever you can to lift the data to a certain level, use some logic or whatever to derive what actions you do, and then act on it. So that person who has to decide what actions to do, that guy is what I call closing the loop. He's the guy who decides what to do, right? And so you want to connect the data to closing the loop. So it's then, what do you do beyond cognition, right? So I have sensory data that's coming, and what in humans is called thought is what I'd like to do. But thought doesn't stand alone. So it's not like you have a bunch of facts that you know and then you derive conclusions. So that's one way to do things, and that's how a lot of theorem proving and all is done, right? Automated theorem proving. What we do is we try to collect a bunch of axioms, we have a bunch of rules to derive new facts, and then we apply it, and then we use methods that will help us verify whether a given statement is true or not, whether it's a theorem or whether it's not a theorem, right? So that's what we'd like to do. But we also have this additional lever when it comes to the real world that we use when we act. So we are not a bunch of people who just sit and then learn everything and grind and then start acting. It's not like that. We constantly experience the world, and part of the reason is that we can never get enough information to say that we have complete information, right? So you can never conclude. Also, even if we had it, the reasoning would become probably so tiresome that it's probably not worth doing the reasoning. You tell a child this is good to do, and then sometimes it will go out and experiment and do something what we think is wrong. It might actually be the right thing, but it'll try to do that, and it'll probably learn something from that as well. So this experience is a very important part that was sort of not explicitly captured earlier, right? And this experience also is IoT driven, right? Because just like IoT is the guy who gives that data, he is the guy who gives this data. So now if we look at this landscape of technology, some of which I talked about, the stuff that mostly concerns data science is on the left, right? Things like learning and predictive and statistics, optimization. And then there's this bunch of stuff on the right. For example, I talked about automated theorem proving, which is purely logical. And so we want to do something between these two, right? Those are the technologies that are interesting to us because we want to be data driven, like I said much earlier, but we want to be able to use a lot of reasoning. So we need to pluck technologies from that side and technologies from this side and put them together. So I'll just skip this example. Maybe if there's time, I'll come back to this. So what we did is, and not just us, a bunch of people have done this before, right? And we needed to do it because we needed to understand what it takes to do that, is we created this little system. So we can feed a behavioral model, right? That means it is a model of the actions, right? Somebody asked what actions. So there are technologies, there's a language called PDDL, and there are other action languages that you can read up about. They can actually model what it means to do something, and it turns out that we're not still very good at that. But anyway, so there are some languages to do that, so we could model your environment, your real world in some fashion, right? And then when you sense something, it tells you how, what's the state of the world right now, and perhaps you can plan what you want to do. So the assumption here, of course, is that this box here is like the little machine that I told you about, right? And the assumption is that it has an intention, it is programmed for something, or it is asked to do a task, right? For example, you can think of a robot which is asked to clean up this room or something like that. So it's given sufficiently high level task, and it's trying to sense the world, and it's trying to figure out what to do, and occasionally it may need to decide something to do, and it may need to compute because it's sensing the world constantly, right? It's doing something and sensing, and maybe it is informed that something is not so okay, so it learns from that, and then it is. So we try to build such a system, and then this was pretty ambitious, right? But then we discovered the intention was not to really build it completely, but to discover all the missing components in order to go ahead and build this thing. So what we did is we focused on the planning side, right? So you look at this picture, we try to focus on this part. In our own work, we try to focus on this part and see what it means to do that, because for us, we felt that this is the part that's taking the feedback from the world and trying to figure out what to do. So there are a bunch of approaches. So this planning is a standard AI technology. It's nothing new. It's been around very many years old, but we never had great methods to do it because of the technology of the times. But yeah, there are some methodologies that we can use. Some of them look like standard optimization techniques. Also, in modern literature, these are called agents, right? That is, if you had a robot to clean the room, it would be called an agent. So we have agents, and learning is about somewhat learning in real time, like creating your models in real time. So how does the agent act in real time was an interesting question that we tried to tackle. And we tackled it to some extent, and I can show you examples if we have time. But more interestingly, I think we are learning that we probably need to go beyond the existing models and go to more probabilistic and more data-driven models. That's where we stand. So for example, we are currently looking at what it takes to do this, learn actions from using technologies like reinforcement learning. Now there's a lot of issues with that. For example, what this reinforcement learning often does is internally it builds neural networks, many of the current technologies. So there are non-neural network methods also to do it, but most of the current technologies which seem to be very successful use neural networks, and then there is an issue with neural networks, and the issue is that they often don't tell you why they did what they did. Okay, so it's like if I used some of the classical approaches and if I derived a sequence of actions to achieve a goal. Right, so remember, we are at the top trying to close the loop. That means we've got some data, somebody has told us make this room comfortable to sit in, and we are going to actuate some things, the AC and something, blah blah, right? And it can actually give you a reason why it's doing that, right? That's what the classical technologies do. But unfortunately, these technologies don't give you that, and the reason why that's disconcerting is that then you're sort of blindly following an advice of somebody that you can't question why he gave you that advice. So it'll be nice to have a proof along with a suggestion. So, that's where that stands. Okay. This is what I told you. So these agents act in an environment, and you observe the environment and you understand what the state is, but you also, these techniques called reinforcement learning, they also get rewards. And so that's what goes into these neural networks. They're sort of feedbacks to the neural network. Just to let you know how there are trivial problems which you have not done very well. So I'm going to give you a very trivial problem, and I'll try to tell you that there are not too many good, efficient technologies to do it. So here are 4, think of them as robots, agents, whatever, and they have to reach, so A has to reach 1, B has to reach 2, C has to reach 3, and D has to reach 4. So this is called the path planning problem, right? And here I have a very simple geometry, but you can think of more complex geometry, right? So even this problem, there are a lot of questions. Do we do this offline or do we do this online? That means, do you have to, for example, are all these 4 told at one time, T0, please, these are your assignments, please go there, right? Or can they come randomly? Like one is asked, A is asked to move, and then a little while later C is asked to move and go to 3. So it looks like trivial, right? At least at the face of it, and we humans can figure out ways to do it, but automated technologies are not very good at this. So they take a lot of time to compute, they're not efficient, they're not even very effective, unfortunately, right? If you try to do it online. So, and then there are a lot of this stuff whether you should actually wait and figure out more about the environment. That's called explore versus exploit, which is assume that you know something and you'll act. You remember sense and act, right? So you act, learn from the environment. So sometimes you should not too much bothered about the environment, then you'll just be reacting to the environment. You won't be doing anything, right? There's a lot of little issues like that. So what I want you to get out of this is that there are very simple problems which are more connected to real world than purely to ontologies or something like that, which are nicely theoretically formulated. In the real world, there are many interesting problems that are easy to state, but not very easy to do. That's because we don't have very good semantics of actions and sensing and the combination of the two. Okay, now a little bit on the device side, because I said IoT and I didn't tell you much about devices. There are a bunch of standards now that talk about how devices should interact. Don't bother about those words, they are just standard names. At the data level, people have started talking about semantics. So there's a technology called SenML that talks about semantics of data. But interestingly, for a person like me who's more familiar with ontologies, this looks like child's play. What they've done is just defined formats, right? And interestingly, what I've noticed is that more recently they've sort of lifted themselves and said, you know, this is not, formats are not good enough. We have to actually associate a formal ontology. So you can, what I'm trying to tell you is that people have been trying to solve what they call semantics and then realize that they need to actually lift the level of semantics, right? And I'm not saying that ontologies are the best thing. Probably we have to go beyond that. Okay, and then you may not have heard of this, but there's this technology called JSON-LD. It looks simple. It looks like serialization of data, but the real technology there is that it talks about how you can take different devices that talk. You know, a manufacturer has his device and maybe formally defines in an ontology, and another manufacturer does it. But I, as the person who's writing an application, need to understand all these things together. So there are a bunch of ways to link these together, and that's the technology that's hidden behind. And of course, people have seriously started doing this sensor ontology. So again, here another interesting thing. So I told you ontologies are nice and everything like that. People have tried to do ontologies. There's an SSN ontology that dates to some close to 10 years ago or something like that, right? And then there was complete peace on that. So nobody was working on that, right? That's because it was not very interesting until people had a lot of devices, which you now have with IoT, right? And they said, hey, no, we have to advance this. This is not where it is. So suddenly in 2016-17, there's a lot of work on this. And the facet that they're working on is trying to describe formally, not with ontologies, but with whatever techniques, somehow we have to say what it means to act on the device. This seems to be the missing facet everywhere, right? So we have elevated some data meaning, but we have not elevated the meaning of action, and that remains a problem. And then there is this nice technology that's called Web of Things is a concept, and they have a technology called a thing description, which actually tries to say in one place, here is how you can talk to a standard, and here is how you can link to ontologies, and here is how you should understand the data that you read from sensors. So all these are sort of nicely coming, and this is probably at the bleeding edge of what's happening in the community. So they're only now realizing that you need to put all these together before you can automate stuff. So we're living in actually very interesting time. And what we are doing is we are thinking about how can I extend this or perhaps this or whatever in order to talk about device actions, right? Okay, where are we? So AI guys will tell you we have done a lot of interesting stuff, and there's AlphaGo and all that stuff like that you would have read about. All that is fine, but really, you know, and they talk about general intelligence and all that little clipping that says that. But really, if you ask the question, are we good at experiencing? I think the answer is still no, because we still don't have good models for what we learn. So we don't have those models yet, still missing the models. And more interestingly, the models that we have come up with that are efficient, like your neural network models or whatever people talk connectionist approach, they don't give us information that we really want. They just somehow this neural network has learned to identify birds or crows or whatever, right? It can classify crows and mynas and stuff much better than a human can, and so forth. But it does not give us, you know, it would be nice if it gave us some information that would inform us so that we could recognize it better, sort of, right? Or we could at least believe what it's recognizing. You know, why do you think that's a crow, and why is it not a man? So we don't have the models that we have. It looks like, and I don't know if this is going to be true forever, right? Maybe we can never understand how we do things, right? And maybe there's discomfort that the machine is sort of learning things just like we learn, which means that we can't explain why something is. You can't explain. You can try to explain, but you probably can't explain, right? So I think we are getting into that phase. So that's where we are, and you know, let's see where we go forward. A little bit of parting note here. So we've been using AI for decision making. Very nice, right? We need help, automation, insights, understanding, recognition. So a lot of good stuff. We've been using a bunch of technologies. Computers are getting faster, and thanks to AI technology, they're getting more human-like. And all this is nice, but I just listed a few. And I really think we should be pushing this, because if you think of all the technologies we have as of date, even that is sufficient to get a lot of value, especially in a society like India, right, where we are probably very good at generating data, right? And we have lots of interesting data, right? You can just ask the meteorological department, or you can just look at the dam data that we have. Karnataka gives data of all the dams and how they're filling up, and you can, very interesting stuff you can do, right? It's just the imagination is the limit, and many of us are so focused on our technology or on our job that we don't take the time to look up. But lots of good stuff there. But there's also a lot of caution, and the reason I bring this up is that there are a lot of very good, very intelligent people who are talking about the fact that there are risks associated with this really cutting edge technology, the cutting part being the interesting stuff there. So it's something to think about, right? Every time you create something really cool, you need to think about it.
Existential threat.
You like that? Or at least it's curious. It's there. So there's always this thing about, about this IT making us not very useful, right? So that's one part of the threat. The other part of the threat is, of course, the fact that one thing is that these guys take automation to the next level and autonomy and stuff. So how much are we useful? That's one part of the existential threat. The other existential threat is the more of the Terminator type existential. I mean, Terminator is a nice guy, but there's this really bad version of that, right? So the point is that if you have autonomous technologies and if you combine it with bad intentions, right, that's not a very good combination. It's like giving nuclear bombs to a terrorist group. So it's possible because a lot of the technologies are open, data is open. So there are a lot of people who are actually AI scientists who are actively working in this community to think about it. So I just thought I would bring this up. Okay. So I've been a little fast, hoping for us to save a little bit of time, but I can take a few questions.
I mean, how do you make sure that real-time learning really works? I mean, you said that identifying a crow, like that machine identifies a crow better than a human does. But how do you know that it's identifying a crow and not just one aspect of a crow that can be in another animal also?
So there are, this is an interesting question. So at least within the data science aspect, they have tried to address it in some way, right? And there are some technologies or some, just like you randomize the data and you do the right things with the data. It's actually data driven, right? So if you give it all the wrong data, then you're going to learn the wrong thing, guaranteed, right? So it's all about giving it the right data, because these technologies themselves are not intelligent to ask you to give the right data, right? They will use the data that you give. So there's always that risk there. And data science is actually a double-edged sword. So, you could use data to interpret the wrong thing always. Even we humans can do it, and sometimes we can do it with an intention to misinform people. So you have to be very careful with the whole data science stuff, right? But on the other hand, what I'm trying to say is that maybe in many cases that's the only option we have. At least that's a very serious option we need to consider. Like I said, the cognition is one thing, but even for actions where we've been working on the action side for a couple of years, and we have realized that unless we take that step towards something like neural nets where they could learn wrongly, right, we probably don't have too many options right now. So
but say if you want to implement these in real time, you're implementing these in hospital systems or all these things, then you have to know, that it is
exactly. So there are two parts to the question, right? That's exactly why all decisions that a system like that makes, an automatic decision support system makes, needs to have this little proof on the side. This is why I think, right? And that is even more serious when you want to make, let's closed loop, right? You get the data and you want to take an action automatically. So now that's really serious, because you are believing everything that's being said. So unless you have something on the side that are verifiable by other means, you're not really closing the loop. You're right, it's an important question.
So I have another question. So what is the reward that you talked about rewarding,
Yeah.
right? So what is the reward that you give to a machine? I mean,
No. So these rewards are just, okay, so I should clarify. You can think of them as costs. They are called rewards because they move the whatever neural net or whatever to another model that is better, but they are all, you can think of them as error measurements or as some kind of a cost of doing something or the value of doing something, cost value. They're two sides of the same coin. Yeah. But that's standard terminology, so I use that. That's all.
and so again, what do you mean by elevating the meaning of act? I mean, act is something that you do. I mean, it's like it can be defined like walking or doing something.
No.
So what do you mean by this word, that elevating the meaning of act?
Okay, so that's a very good question, and I don't think I have a complete answer, but I have one answer to it, which is what we are doing. So what you'd like to do is, unlike a neural network which can learn something and you don't understand, when you say elevate a meaning, you need to have a model for that, like a formal model for that, which you can reason about. So are you familiar with PDDL or not? Okay, so one model is PDDL, and for those of us who don't know, I will just repeat. So it's a model where you have an action, and in the action you can say what are the preconditions under which this action can be taken. So for example, let's say lifting this is an act I can take provided this is there, right? If it's not there, I can't take it. And when I lift it, then the state is that this is in my hand. So it has an effect, right? So there's a precondition effect. So in simple terms, an action can be defined by its precondition and its effect.
And so, sorry, the last one. So what are the morality risks of this? I mean, you talked about them, you didn't discuss that.
Which one?
The morality risks of this. Last slide. Continue.
So everything that every nice technology like the internet has an immoral aspect to it, right? We all believe that, right? We all see that, right? So unless we believe that we need to do it for the right purpose, every good thing that we can create can be taken for the wrong purpose. And here you're building something that's really powerful, right? So you need to be very careful. That's all.
Yeah, I have just one. Yeah. If you try to position the current technology and its achievements, much of the work has been, the achievements have been empirical, and even very simple things like the performance in something which is not in the test set, really for a sufficiently complex classifier is really not mathematically predictable and countable.
Yes.
We do not have the mathematics for high dimensional dynamical systems.
Yes.
We don't even know what that would be actually.
Yes.
So is it fair to say, and to get to say something is AI or intelligent, when we haven't even defined what Asti is?
What?
Asti, when does the brain, human brain say there is something rather than there is light or sound and so on?
Yeah, I think these are good questions. So
is it fair to say that we have seen examples of capabilities, potentials, but it would be essentially a long journey before we can say we have sufficient, something which we can call or which we can say is mock-up intelligent.
Yeah,
As of now, I would say, what would you say, that a large number of the achievements in the recent past have been generalized least-squares.
So I think you're right. Generalized least-square is a very nice way to put it, actually. So you're talking about the error and minimizing error and all that stuff. Yeah. And that's why I often think of these as, artificial intelligence might be too big a term to use. So I often think of this, if you see my first slide, I used an autonomous system thing at the bottom. So I think of these as even if we built an autonomous system, right, it need not be intelligent. If you build an autonomous system beyond what today's control theory builds for us, right, that is a lot of achievement for these formal methodologies. Because what is an AI is still very difficult to talk about, right? We can't define it, right? Well, we don't even know the definition of what is an, can we compare, unless you go to Turing test and so on and so forth, which is another way of looking at an AI. Like,
in fact, I don't know whether you would agree that you would probably see the synthesis of religion and science, because these complex systems are so complicated, are sufficiently beyond the small dimensional mathematics we can analyze, that societal experience over millennia is the only tool we have currently to have safe predictions of the utility and behavior of such systems?
So I think we need to be clear that as long as we think of limited domains, we are okay. Right? So we should not, we are just trying to push that limit every year, that's all. But we are not, we don't even know what the bigger target is. We are just trying to push the envelope of the domain that we can do. And we need to see it sort of as an effect of where the technology stands today, and the technologies of tomorrow taking us a step forward there. But if you think about the philosophical aspects, there's a lot of interesting questions there, which, like I said, my talk was very technology focused. I don't want to get into that part, but it's very interesting and very relevant, especially for an AI discussion, right? So we need to really think about the philosophy behind that. So I don't think I'm even qualified to come anywhere near that. But my vision is that there's a lot of good stuff to be achieved by putting together technologies to advance where we are in terms of autonomous systems.
Thank you, Dr. Badrinath, for giving us a very enlightening presentation.